Hello everyone, this is Dilleswara Rao. From my Aeronautical department. From our last few classes, we are discussing on automatic control of aircraft subject for BTech undergraduate program. In the last class, we have discussed on stability augmentation system types and what are the system importance and how that stability augmentation system is being installed in aircraft in aircraft control system for controlling that total aircraft control surfaces, how this stability augmentation system is being installed, what are the things involved on that one. Also, we have just given some explanation on last few classes. So now we are discussing on significance of stability augmentation system. So significance means it's we are discussing some uh, applications of this stability augmentation system in the aircraft controlling objects. So now let's see the topic. Here we are explaining this SAS system with two examples. Like examples means these are all applications of aircraft only. So these two applications will be this the effect of pitch rate and alpha feedback and washed out alpha feedback example. With these two examples, we want to explain about this SAS system. So why this what is this explanation and why we are using this one, and what is the significance of this SAS system for installing in aircraft, and why we are using this SAS system for making that completely stable, and how this stability system of aircraft will be like we are using for further application. Like when we just we said, like in the previous classes, SCS system means that aircraft, when an aircraft is in unstable condition, this system will help that to making it in stable condition. So we have just we in last two videos, if you see, there I've explained in two parts for this SAS system. So what is this things involved on pitch controlling system and lateral directional controlling system, also how this SAS system has been installed, and what is its importance also we have already discussed. So here with these two examples, like the pitch rate and alpha feedback effect, and washed out alpha feedback effect also, we just want to explain you like how these things are being involved on controlling this SAS system and design of this SAS system for controlling surface. So let's go into the topic. So the configuration of this pitch stability augmentation system has been given here. I think you have seen this one in last classes also. Like again, generally the system will contains the summing amplifier and an integrator. That's like a transfer function only. After the transfer function, in stage summing amplifier will be there. From that summing amplifier, another transfer function of this pitch rate transfer function, and that transfer function output will be given to that aircraft dynamics model. So from that, there are two feedbacks, like pitch rate and angle of attack, that alpha rate also we have given to that summing amplifier. These two feedbacks, what is the significance of these feedbacks only we are going to see now. So see here that aircraft dynamics to illustrate the effect of pitch rate and alpha feedback. So the aircraft dynamics will be augmented with actuator and a noise filter modules. So these will taken from original F-16 model report. To see this report from the reference that Nguyen et al. At 1979. So the both simple lag filters with time constant TA will be around 1 by 20.2 seconds. This is 1 by 20.2 seconds, and TF will be 0.1 second for that time response. what is the things like the report, I mean the model report have been installed at that time in the F16 model. We can see that in that report. So that gives you like the argument. I mean that gives you dynamic results with the two types of matrix things it can be explained with two matrix. So that's like x dot matrix is there here now. So in this that A matrix and B matrix are there with respected values of tau, and the variables matrix is there here now. So this has been explained in terms of matrix level only, and with respect to that values, what are the outcome values for y rate also we have given here. So here you see the original state equations are still satisfied, and the original delta E input that is delta E means elevator input only. Now connected to the actuator alpha, the that is actuator state alpha, and that is being given by the velocity UE, that elevator, the velocity in x direction. Also, the filter is being driven by that alpha f. That alpha f is the state of dynamic, that is angle of attack of angle of attack at state dynamic state. And the additional output also have been given for a filter signal, that is XA. So this is in the x direction variable, that is for the feedback only. The state of equation could also be created by the simulating the filters as part of aircraft model, and running the linearization program. Like linearization program, if you see in previous things, that how that linearization program, like the thing, I mean the control surface program may be designed to make that integrator and the transfer function solution also. I mean, that solution means that is the output value, that output frequency value given to that control surface. So that the state of equation can gives you the two things, like that can be used for obtain the loop transfer function needed for root locus design. And in this case, the innermost loop, we already know that the loop transfer function will consist of two lag filters in cascade, and the effect of the feedback K can be anticipated using the sketch of pole and zero position. Like a pole and zero position means it's like a neutral position only. Pole means when we are giving that angle of attack to that control surface. Like here we are trying to see that inner loop and outer loop transfer function. Like when we are explaining this with this root locus diagram. That root locus diagram will give you the different input values, how that output signal is been varying with respect to that imaginary axis. So if you see that in previous things also, for different for the different inputs, how the transfer function values have been given for that control surface input. So that we have already discussed in a few classes also. So that the goal of that alpha feedback is to pull that unstable pole at s equal to 0.098 second, 0.098. So back to the left half S plate. According to the root locus rules, that locus from pole will be moved to left along with the real axis if the static loop sensitivity is positive. That means that static loop sensitivity, if you see that figures in here, that static loop, that real axis for S plane, the root locus for A and B, we have seen that left values have been pulled. See here that left along, I mean the pole will move to the left along the real axis if the static loop sensitivity is positive. Like left along axis means which one? So this is being going to that left along the imaginary axis only. So that means axis means that values of that values far away from that imaginary values. So so that the static loop sensitivity resulting from transfer function shown below is negative values. We are getting that transfer function for that angle of attack to that elevator input transfer function is given here now. So that these two graphs, that graphs means these two root locus plots, we got it from by using this transfer function, that alpha by delta E will be equal to 0.1232 into s plus 75 into s plus 0.009820 plus minus g into 0.09379 by s minus 0.09755 into s plus 1.912 into s plus 0.1507 plus or minus j into 0.1153. So this transfer function will gives you the values for after solving this transfer function with Laplace transform. So we will get the values for s for different values. For different input values, that s values we will get it with imaginary axis and the real axis, where we will plot the values in between that imaginary and real axis. So see here that the locus has been going left side of that imaginary axis. So that is going to be negative values only. So that only here it is showing that static loop sensitivity resulting from the transfer function is showing negative values only. So that negative values of k will be used for root locus program. For that, for deriving the values for k, we are taking that negative values only. So that figure 2a and b, like here you see that figure 2a and b, so shows the root locus plot for inner loop and inner loop for two different scales. That expanded scale near to the origin, like see that expanded scale near to the origin means when it is going from near to this origin is there, no, that expanded case. So that shows the effect of alpha feedback to make the Loki from third mode poles come together on the real axis. So the branch going to that right then meets the branch coming out from unstable pole, and they leave the real axis to terminate the complex zero near to the origin. Like here, the branch going right, to the right, and then meets to that branch coming from unstable pole. So that unstable pole is what? That unstable pole means this imaginary axis values only. And then they leave the real axis to determine the complex value near to the origin. Like when it is going near to that things means here the values are getting more negative. So when if it is the values are more negative, then it will approach to that that origin zero only. So this provides the closure loop poles that corresponding to a guide mode, and the left branch from the third mode poles meets the branch from poles at S 1.9. So for these values s 1.9, and they leave the axis near to s equal to -1. So from the short period, here the values are giving for a guide mode only, but if it values leave that at -1, so it will be turning to short period mode only. So that alpha feedback has been therefore anticipated, gives the anticipated effect, like the aircraft is stable with the conventional longitudinal modules. So that larger scale plot, like larger scale plot, if you see in the 2a, so shows the magnitude of alpha feedback is being increased. So the frequency of short period poles are increases, and they move towards right half plane. So that movement towards right half plane is due to the repulsion effect of filter and actuator poles out at s equal to 0 and s equal to minus 20.2. The effect of short period locus is relatively small, because when they will go to that left of that S plane. So that left of that S plane, if you see here, that left of that S plane, if you going there, so for that the transfer function, it will it will follow the transfer function with respect to the velocity will be that q by u equal to minus 203.2 into s plus 10 into S plus 1.027 into S plus 0.02174 by S in S plus 20 into S plus 10.89 into S plus 0.69 plus or minus J into 2.303 plus into S plus 0.008458 plus or minus J J 0.0869. So this transfer function will gives you that a higher short period frequency to be achieved. Like a short period frequency will get it from the above transfer function will be high. So the position of the short poles for K alpha will be minus 0.5. That is plus that imaginary that the complex function will be like minus 0.7 plus or minus j 2. So at this position, the natural frequency is about 2.2 radian per second, which is acceptable according to the flying quality requirement. But the damping ratio it is showing like 0.33. So it has been somewhat quite low only. The root locus problem, a program for this transfer function will determine the effect of pairing KQ with the K alpha and that is being fixed at minus 0.5. So that the Q by U transfer function with the K is minus 0.5 and KQ is 0. Then the root locus thing for that transfer function will be given here only. So make sure that the previous root locus function is depend on that transfer function that has been given here only. This is the transfer function for this root locus program, and this is the transfer function for this root locus program. So here that root locus means we are solving that S values with actually these S plane values will be contained that imaginary values and the real values, because it's a complex values only we are getting from that solving that equation only. So that complex values will be taking it in y-axis and real values we will take it in x-axis. So the zeros of this transfer function are unargumented open loop zeros with the addition of that 0 at s equal to minus 10. So this 0 is originally cancelled the alpha filter whole out of pitch rate transfer function. So that loop feedback has been now moved to that alpha filter role that is s equal to minus 10.89. So that below figure 3 you see that figure 3 shows the root locus for negative values of KQ. Like that KQ values have been showing that negative values only. The short period poles are follow that approximately that circular arc. That circular arc is there, no? So this circular arc. So that constant natural frequency increasing damping as the pitch rate feedback is been increasing. So when the pitch rate feedback is been increasing, like the feedback values have been increasing so much, so that natural frequency and the damping will be constantly increasing. When this pitch rate feedback, like pitch rate feedback KQ and K alpha, if you see here, so here that K alpha and KQ, so that these are the two pitch rate frequencies and feedbacks, and for the feedback one controlling transfer function also is there, that is the GF only. That GF means a filter noise filter transfer function. So that has been given previously. So the this GA and GR we have already given, like these are the aileron and elevator transfer function. Here it is like it is pitch rate, so that elevator transfer function only we will get it here. So that elevator transfer function is being given here, and that filter transfer function is being given here. So based on this, that KQ values have been when that feedback values have been increasing. So see here that that constant arc will be gives you that frequency and damping ratio effect only. So when the pitch rate is being increased, so that the short period poles follow the approximately that this short period poles are there. No, this will follow this circular arc only. That means that natural frequency and damping will be constant. So the poles become real, quite low values for KQ, and the larger values near high frequency oscillatory modes have been created by the filter and actuator poles. So such values of KQ are probably not feasible design because that actuator rate limiting would be prevent the system from following a higher frequency mode. Like when the values of KQ have been probably not feasible, like these are not acceptable values when the actuator rate is being limiting would prevent the system from higher frequency. Like when the frequency rate which been higher, then the controlling also will be become more unstable on it. So to avoid that one, that KQ values will not be go beyond that design the values. So furthermore, that slow pole created from the short period pole may contribute significantly to the response, that frequency response. So therefore, that selecting values for KQ, which will be like a 0.25, that places the short period poles will be like that. There the S value will gives you like 2 - 2.02 plus or minus J 1.94. So that means we are getting that value imaginary values of it. So how these imaginary values we will get? If you see when that equation, suppose that s square plus as plus c equal to 0. So generally if you want to solve this equation, how we will solve that? S will be equal to minus b plus or minus root of b square minus 4ac by 2a. So generally these values only, this formula only we will use it for solving the roots for s. But here, if this value, that b square minus 4ac is less than 0, if it is less than 0, then we will get the imaginary value, no? Like a root of minus values only, minus 1 or minus 2 will get. So then here, if it is a minus value, so then that will be like minus b plus or minus j, j1 or j2, like that it will come. So like suppose if it is minus minus root 2 means what? Minus root 2 means 2i. I mean 2i or 2j. Generally, we will make it like a 2j. So that will be minus b plus or minus 2j by a. So this is the values we will get for yes only. That means here we are getting that values for yes is in complex form. That complex form only we are getting the rules. I mean here only one function is there. Then for that one function we will get the roots like this. If functions are more, like we said, s power 4 and s power 5 is there, then that I mean s power 5 means what? S power 4 plus s cube a1 plus s square a2 plus a3 plus c equal to 0. Yeah, this much a big equation is there. Then we will get four roots only. So that four roots you can see here. These are the four roots. On that two roots are imaginary roots only. I mean here plus or minus two roots are there. So that means six roots are there. Maybe that equation we will get it in six roots. One plus value, one minus value means six root value only we will generally get. That means, I mean, I'm just giving you that how these imaginary values we are getting for this S function. So here you see that S is having minus 2.02 plus or minus J 1.94. This corresponding to that natural frequency value, we will get it 2.8 radian per second with a damping ratio of 0.072. That means that damping ratio has been somewhat high. So that corresponding to closure loop transfer function pitch rate, that the closure loop transfer function pitch rate for this one is take it from here only. So that original actuator pole moved from minus 20.2 to 16.9. A filter pole has been moved from minus 10 to minus 11.88. So here for this also we can draw the root locus function. So that root locus function already we have given here, that figure 3. So this is like how these values, like minus 10 to minus 11.88 it is shown now. So when that S value is moved from minus 20 to plus 16 point, like minus to negative to plus value it is going, then the root locus values will be changing from minus 10 to 11.88. That is been going to that negative loop only. So here you can see the both the feedback gains are negative, and when the negative sign at the summing junction, like in figure 1. So see here, then figure 1, that summing amplifier is there now. So this is the summing amplifier. So uh, so that summing amplifier is taken into account. So this means the increasing pitch angle, increasing alpha, both will gives you an elevator. Both you gives you a positive movement for elevator, like a positive displacement. Like when that increasing in pitch and increasing in alpha, like that if the alpha values are increasing or the pitch rate is increasing, obviously that elevator displacement will be increased. Like you see that positive that elevator movement is there now. So if it is the elevator movement and this elevator is being going to the top, that means when pitch rate is up, means this displacement from here to this displacement will be goes on increasing. So that has been practically also we can see from if you see it from drone operation or a or any normal UAV operation. If you see when that elevator displacement is been increasing, so I mean when the pitch rate is increasing, that elevator, that means here the feedback loop is there, no? When the feedback loop will gives you how much value we will give it for that elevator displacement. So when the pitch rate will gives you like a feedback only, like this much value you can go forward, some more value you can go forward. So when these values have been going forward by these feedback values, so that the displacement control surface also will go on increasing only. So according to that sign convention, if you see in previously, so this is a positive sign and this is a negative sign. I mean, if it is going top only, if it is going top side, then it will be positive moment. If it is going downside, it will be negative pitching moment. So positive pitching moment and negative pitching moment. So if you refer that table in a previous video, so that creates a nose down pitching moment. This is a restoring moment, and therefore the feedback polarities arrived by the straightforward application of root locus principle agree with the physical interpretation of feedback requirement. So when we are keep on increasing that one, so that that feedback will gives you it should be it has been reached to maximum value, so that the maximum that nose down pitching moment should be come. So that means what, when this elevator is been up, and if it is going to the down, I mean due to the feedback signal it will be going down. So when it is going down, then that nose down pitching moment will occur, like when it is going like this, and then it will be like if it is a stable condition, I mean if it is a cruise condition, it will be go like that. When an elevator is been applied, so that it will slightly the pitch rate will be I mean slightly the pitch rate will be go on, and then immediately when the value reaches that maximum value, immediately that elevator will be goes down. So due to that the down moment, this nose down moment will come. That means the negative moment will come. Then for taking that into stable condition, it has to come to that negative moment only. It has to come, like it has to take that negative moment only. So that means when the values are being going from negative to positive, then the values are going more to that imaginary axis. In the root locus, if you see, that values are more going to that imaginary axis. So that means what, if it is need to be stable, then the values should go to that negative values only. That means that is why that previously if you see that values is there now, so it has been taking from minus 10 to minus 11.88, when it is going from minus 20 to minus 22 plus 16.3. That automatically it is attaining that values. So I mean, that means what? that physical interpretation of that control surface also, that physical interpretation of that control surface also is been given here. Okay. So the ability of angle of attack and pitch rate feedback will allow that short period poles to be positioned with low has been demonstrated now. Like this pitch rate and the negative that angle of attack significance also been given with that root locus things only. So when the basic airplane is been stable in pitch and the desirable short period poles location may be achieved with pitch rate feedback, then that eliminates the alpha sensor. Like when that pitch rate and the desirable short period poles have been attained, so the pitch rate feedback will be achieve the values which will I mean when that the values have been sometimes I said if it is need to be go beyond that design values. So if it is need to be beyond that design values, so it should be go beyond that desired default values also. That means that alpha sensor values, I mean sometimes that alpha sensor signal may be eliminated and that required operation, because it should be bring back to that stable condition, means that sensor things should be bring back. So that integrator was assumed uh, assumed to be present reference to the SAS system to provide the angle of attack reference only. So this is not a practical arrangement unless that the outer loop is being closed around the integrator. So we can say like that SAS would not be considered practical for an unstable aircraft. SAS alone, like SAS alone means only here SAS alone what it is showing, I mean what it is doing that when that airplane is going to that unstable condition, it is making that airplane to come to that stable condition. I mean the SAS system is used for making that into stable condition only. But sometimes in a higher pitch rate, this SAS system will stop that the pilot to take that higher values. So that means this SAS system also will have some controlling agent, because this SAS system is not allowing that system to operate for higher value. But in a emergency condition, suppose when an aircraft is landing on the airport, so when it is getting more negative values, but more negative values means this SAS system will gives you warning only, because it is getting more negative values only. It will make that it will make that aircraft to make it in normal position, but that is not desirable in at landing, no. So that times means what, there will be a controlling agent to control that SAS element. So in somewhat a layman approach, if you want to say, so in a layman approach, if you want to say, everybody is using antivirus software. Like if you are using any antivirus software, so sometimes this antivirus software will detect everything, whatever connected that pen drive or maybe hard drive. If you are connected to that system, this will this will gives you one warning system that one external device is being connected, whether it is need to be scanned or not, that scanned value scanning is required or not, some warning message will be given now. So like that, I mean that time what we will do, if it is we will know that already it has been used many times, so there is no need. So that time what we will say, not now, that option we will check, no, not now option is there, no, that not now option we will press, so that checking of the disk will be avoided. That means that skipping of that we will skip that thing. So like that here also, for an every aircraft, whether it is a passenger aircraft or a jet aircraft, this SAS system alone is not, I mean, only making this SAS system installation will not gives you the controlling, total controlling of aircraft. So there will be a controlling agent for this also. Sometimes we need to we need to skip that values coming out from the SAS also. So that means that is why they are giving like, therefore that SAS alone would not be considered practical, would not be considered practical for an unstable aircraft. That means practically we will not consider we will not consider this SAS system only that controlling system for making that unstable aircraft to stable condition. So another example, like I said, no, previously pitch rate and alpha feedback system we have used now. Another thing will be like pitch essays with washed out alpha feedback. So washed out alpha feedback. That washed out alpha feedback. That washed out alpha feedback you can see from this one. So, the table, if you see it on, if you refer that textbook, I will refer you. So, it is included that alpha feedback shown in figure, that figure one we use, that the steady state angle of attack, which will develop a steady voltage across the washed out circuit capacitor. So, the angle of attack changes with which are fast relative to the time constant of that washout feedback will directly will fed back directly to the elevator actuator only. So thus achieving the desired instrumental alpha feedback. That means that instrumental alpha feedback if you want to get, so that will be directly fed into that elevator. So that will gives you that thing. So if the coefficient matrix are in example, previous example is there, no? So in a previous example, if you see that if a coefficient matrix in that previous pitch essays with alpha feedback is there, no? So for the washed out circuit, how that coefficient matrix will be, we can write it like, you see the difference between previous and this one. So here this 57.3 and indicate the radians to degrees conversion, that will be like a 57.29. That means 57.29 we have write it like a 57.3 only. So for a 5s washout time, that is chosen as K alpha and KQ are again set to minus 0.5 and minus 0.5 and minus 0.25 respectively. So for that, the closure loop pitch rate transfer function will be, if you see the transfer function is given like this. So that is minus 203.2 into S into S plus 10 and S plus 1.027 and S plus 0.02174 into S plus 0.2. I mean S plus 0.2 by S plus 16.38 into S plus 11.9 into S minus 0.02 into S plus 2.072 plus or minus J 2.04 into S plus 0.54 plus or minus J 0.713. So these values we will get it for the transfer function. This transfer function is closely related with the transfer function 3 that has been given in previous, no? That is what here, that this transfer function is there, no? This has been closely related with this one. Apart from that, the zero created by the washout alpha feedback loop and the unstable pole set as 0.2, and when as 0.2, that unstable slow poles we will get it at this value. So that unstable poles comes from the original pole at s equal to 0.098, which will now unable to move that aircraft left, move that to left half plane, because the washout zero at the origin, because washout zero at the origin. So the unstable expansion mode corresponding to the pole is now slow enough to that pilot slow enough. So that will gives you that pilot to easily control. But it depends on the thing. But it gives you one inconvenience that that makes this approach unlikely to be used, because while we are using this one, so there are many adjustments have been given here. So mostly this may be used very limitedly. So I mean, here you see we have explained that SA system with the two examples. Like one is with the pitch rate and alpha feedback transfer function. I mean alpha feedback device, and another one is pitch rate with washout alpha feedback thing. That washout alpha feedback and this with the alpha feedback thing. So here these two values, I mean these two what it is giving, like when you are applying that SAS to the control system, how it is been behaving, and while you are using for that control surface augmentation means it's like a making that into in control. So when we are using this SAS system for different control surfaces like elevator and aileron, and for a lateral motion aileron and rudder if you use, and for a pitch motion and axial motion you will use for flaps and elevator. So when you are using that values for that one, I mean when you are installing this SAS to this control surface, how that control surface movement frequency is being getting by using different integrators. So that only here it is showing like this transfer function will give, it's like integrator function only, that IC function only. This IC function also will be depend on that summing amplifier voltage, and that signal comes from that controlling stick is there, no, from that controlling stick how much signal is being coming out and how these values are been taking out. So this has been depend upon that signal coming out from the pilot, and the transfer function signal, the transfer function output values also. So we cannot make this transfer function for our benefit. So it has to be benefited when we are checking with how that control surface will behave for a different types of inputs, for a higher inputs, for a lower inputs, for a negative moment, for a positive moment, for a negative negative rolling moment or positive rolling moment. How these control surfaces are affecting that stability of that aircraft. So for that explanation, how that electronically that control surfaces have been controlled by using these feedback functions and transfer functions and the integrator functions, how we can use that. For that purpose only we have given this one. So this is all about stability augmentation system significance, that significance of SAS system. So for that, I've used the textbook, this one. So Stevens BN. So if you can refer the further for any clarification is required, you can refer these books and other online videos also. So please do watch my previous essays videos also for better understanding. So there is an interlink between everything, between while we are focusing from one part means there has been interlinked to every following thing also. So that's all about SAS. In the next class, we will see it about control augmentation system. So that's all about this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.